Hello friends, today's question. A thin fixed ring of radius 1 meter has a positive charge 1 into 10 to the power minus 5 coulomb uniformly distributed over it. A particle of mass 0.9 gram and having a negative charge of 1 into 10 to the power minus 6 coulomb is placed on the axis at a distance of 1 centimeter from the center of the ring. Show that the motion of the negatively charged particle is approximately simple harmonic. Calculate the time period of the oscillations. So we are given that there is a ring which is something like this, and on the axis of the ring a charge is placed, negative charge. So this is our negative charge and its value is given as 1 into 10 to the power minus 6 coulomb, and on this ring a positive charge is uniformly distributed. And its value is given as 1 into 10 to the power minus 5 coulomb. And the distance between these, the center of the ring and the charge, is given as 1 centimeter. So this is our 1 centimeter. So before we can we are going to use directly the formula for the electric field at this point, find out the force at this point, and accordingly we are going to just manipulate a little bit, and we are going to get the equation which states that the negative charge is approximate SHM. So let us start with the electric field on the axis of a uniformly charged ring. Okay, so this is a uniformly charged ring and this is the axis point. At this point called as P. So you can say that electric field on the axis of a uniformly charged ring you can write the formula that the electric field on the axis of the ring at a distance z from the ring center, and we let the r with the radius of this ring. So this electric field, let us suppose, is given as electric field at a distance z, which will be equal to k charge multiplied by distance z divided by r square z square, and we have it is 3/2, and k is the Coulomb's constant, and which is 9 into 10 to the power 9 Newton meter square per coulomb. So we can find out the force acting at point P. You can say force on the negative charge. Force on the negative charge. And we assume that this negative charge is denoted as small q. So you can write the force acting on the charged particle on the charge particle with Q charge. So we can write F will equal to minus Q multiply electric field at point Z. So we know the value of Ez. Therefore we can write that minus Q, this comes K Q multiplied by Z divided by R square Z square and by 3 by 2. So we can make an approximation that the value distance of Z, or we can say the Z is very much less as compared to R, because this Z, this is our Z, and it is given as 1 centimeter, whereas the radius is given as 1 meter. So in compared to radius, the value of Z is very small. We can make the approximation. So we can write it as approximation of small distance, approximation of small distance so we can say for a small displacement along the axis, Z is very small than R, because Z is given as 1 centimeter, whereas R is given as 1 meter. Therefore, we can write that the denominator R square plus Z square can be approximately equal to R square. So based on this approximation, we can remodify the equation of the electric field, and that we can write K Q Z divided by this becomes R square, and we have here 3 by 2, and this will be K Q Z, and we have our R cube. So therefore we can write force will be equal to minus of Q, and this becomes now K Q Z upon R cube. So based on this equation, we can clearly see that our force is directly proportional to inverse of the distance. So it means force is opposite to the displacement. Force is opposite to displacement, and which is nothing but a representation of SHM. A representation of SHM. So we just proved first part, that it will be executing SHM, or approximate SHM rather. Okay. Next we are supposed to find out the time period. So we write the equation for the motion. Equation of motion. So you can say the particle with the force F, the particle with the force F will be equal to mass into acceleration, and that will be equal to mass multiplied by double derivative of the displacement, that was our Z. So we have two equations for F, first equation and second equation. These two equations we can say, let me call this as equation number 1 and this as equation number 2. So we can write from equation 1 and 2. From equation 1 and 2, we get m double derivative of z is equal to q, and we have k q z upon r cube. So therefore from here we can write that our double derivative of z will be equal to q k capital Q, and this is mrq multiplied by z. So forgot to mention minus sign, and which can be written as, because for SHM we have that double derivative of z is equal to minus omega square multiplied by z. So making comparison 1:1, we can say our omega square is equal to q k capital Q, and this becomes r cube. From here we can say omega is equal to square root of q k q upon mr cube, and we are supposed to find out the time period of oscillation. You can say time period of oscillation, which is given as t, is equal to 2 pi upon omega. So this gives us that t is equal to 2 pi square root of mr cube qk cube. Substitute the value 2 pi square root, mass is given to us. Mass is given as 0.9 gram. So this will be 0.9 into 10 to the power minus 3. Radius is given as 1 meter. This is 1 cube divided by, and we have charge, that is 1 into 10 to the power minus 6. K is a constant, that is 9 into 10 to the power 9, and the charge on the ring is also given as 1 into 10 to the power minus 5. This gives us that t is equal to 2 pi upon 10, and which can be approximately equal to 0.628 seconds. So this is the time period of oscillation. This is the time period of oscillations. This completes the question. Thank you.